All right, we're going to look at a system for drawing what are called Lewis structures for molecules. Some of you may have learned how to draw these, or at least be somewhat familiar with these from a high school chemistry class. If you learn to draw these by some other method different from what I'm going to explain, that's fine, as long as you arrive at the same structure in the end that I do. Okay. The way I'm going to present this is in terms of something that's pretty close to an algorithm. It's how we do it in the textbook. It's meant to be a systematic way that just says if you always do this, you should always arrive at a structure that we're going to be able to work with. So down in the bottom corner there, I put a picture of a Lewis structure. This down here, this is a molecule generally referred to as phosgene. It could also be called carbonyl dichloride, I suppose. And that's what a Lewis structure looks like. Okay, so it's a collection of lines and dots, basically. And what those lines and dots do is they represent the valence electrons in the molecule. The valence electrons, remember, from each atom are the ones in the highest filled energy levels, right? And it's pretty easy to find out how many valence electrons an atom should have by just counting across where you are in the periodic table. These structures are pretty easy to draw, frankly. You should not feel too troubled by them, but they turn out to be very useful for describing the bonds in molecules, okay? In this picture, one electron is equal to one dot. So every place I see a dot, I see a valence electron, right? And if I have, where I have pairs of dots, that means I have a pair of electrons, right? The lines represent shared electrons, and each line represents one pair of shared electrons. So down here, where I've got single lines between my carbon and my chlorine, that means there's one pair of electrons shared between those two atoms. Up here, where I've got two lines between the carbon and the oxygen, what we'll call a double bond, that means I have two pairs of electrons in there, right? Because each pair of electrons forms what we'll come to call a bond, and what's represented in the picture by a line, okay? To count the valence electrons, really, you just count how many come from each atom. So if I was drawing the one that's down there, the carbon would come with 4 valence electrons because it ends in S2P2. The oxygen would come with 6 valence electrons, and each chlorine would come with 7. And I have 2 of those, right? So that's 14. So altogether, I should have 24 valence electrons. And if I count in my picture, I get 2, it's going to look like those are more dots. Okay, so I get 2, 4, counting the pairs there, 6, 8, 10, 12, 14, 16, and then I have 4 lines, which is 8 more, so I get 24, right? So all my electrons are in my picture, confirming that my structure is okay. What I'm going to do in this video is first I'm going to explain a set of rules, and I'm going to illustrate them by just drawing structures for a few examples. And so let's just dive into that. These are my rules. The first one is I'm going to look at the compound I'm drawing a structure for, and I'm going to decide, is it ionic? And in particular, does it include polyatomic ions? If I conclude it does, I'm going to take those ions and I'm going to draw a separate structure for the anion, the negatively charged one, and the cation, the positively charged one, right? Lewis structures are based on representing shared electrons, and so they're not good at describing ionic bonds. I'm going to count the valence electrons in what I'm drawing the structure for, so I know how many electrons I'm working with. Then I have to draw a skeleton for my molecule, okay? And I'll explain as I go through some examples, some ways to get started on that. Once I decide how I want the atoms arranged, I have to put at least one bond to each atom to just make sure it stays attached and doesn't fall off, okay? That'll use up 2 electrons for each bond that I draw. So I'll go back to my total count of valence electrons, I'll subtract however many I've put in so far and see how many I have left. Then I'm going to start with what my rules here call the outer atoms. Those are the ones that are only attached to one other atom, okay? And I'm going to start by placing 3 pairs, 6 electrons total, of non-bonding electrons. Those are the ones in the previous picture that were represented by the dots, right? So if I look at my structure here, the ones where I put the check marks by them that are drawn as dots, those are what we could call non-bonding electrons. We'll also often refer to those as lone pairs of electrons, pair because they usually come in 2s, lone because they're just on a single atom. Exception to that is if hydrogen is one of my outer atoms, hydrogen always only gets 1 bond and nothing else, just because with only 1 proton in its nucleus, you can't really fit a lot of electrons around that single proton. After I've done that, if I have more electrons left over, I'm going to just put them onto the inner atoms, any atoms that are bound to more than one other atom, or the one in the center if I've got the kinds of simpler structures we'll start off with. When I get to there, I've got a structure drawn, and it should have all the electrons in my picture, okay? It's not necessarily the best structure, so next I have to check and see, do I think that's the best structure I can make, or is there a way to make it better? So I say I'm going to optimize the distribution. If the atom in the center of my molecule is from the second row, which it often is, because that gives me carbon, nitrogen, oxygen, things that are very common elements, right? Then I'm going to follow what is called the octet rule, which says I want 8 electrons around each atom, okay? Again, exception generally being hydrogen, which is always going to have just a single one bond, okay? If my central atom is from somewhere deeper into the periodic table than the second row, typically starting somewhere around, I don't know, like phosphorus, sulfur in there and going down towards the bottom right-hand corner, then we could sometimes have more than 8 electrons around that central atom. For our purposes in our class, we're only going to do that if there's no other way to draw a structure, right? If I just have so many electrons that there's no other way to put them someplace except to stick more than 8 on that central atom, and then we'll go ahead and do that. Lastly, it says we're going to check for equivalent structures, what are called resonance structures, and we'll talk about that at the end of the video. So let's just do some examples. We're going to start with a relatively simple one and work our way up. Not that any of them are terribly complicated, but the first one I've got on my list is just methane, CH4, okay? If you had a periodic table nearby, you could just count columns across to carbon and say that the electron configuration for carbon ends in what, 2s2, 2p2, those are its valence electrons. So the carbon, I have 1 carbon and it's got 4 valence electrons, so I get 4 from carbon. The H's, I have 4 H's and each one has 1 valence electron, so I get 4 there. So I have a total of 8 electrons. I have to draw the skeleton or this just general layout of atoms for my molecule. In this case, it's pretty easy because hydrogen can never go in the middle, right? In most of the structures that you'll be drawing in our course, you're going to have one of something and then some number of something else attached to it, okay? General rules of thumb, the thing there's one of is generally going to be the one in the middle. It's also true that the atom with the smaller electronegativity will usually be the one in the middle. Again, in this case, we don't really need those rules. We're going to say, well, it can't be the hydrogens, right? So I'm going to put the carbon in the center. I'm going to place the hydrogens around those. And we typically do this sort of using the sides of a square. Although there's nothing really special about the different positions. I need to attach each hydrogen by at least 1 bond. And since they're hydrogens, by exactly 1 bond, right? When I do that, I've made 4 bonds. So I've used up 8 electrons. So I have no more electrons left. I can't really move any electrons there because I can't move an electron pair without breaking a hydrogen off, right? My carbon has 4 bonds around it. That's 8 electrons. That's the octet rule, right? Notice that also follows the rule we used when we were drawing line structures. It said a carbon always got 4 bonds, okay? That's really just a specialized version of my octet rule. My hydrogens all just have 1 bond, so that's my best structure for methane. That's really a simple one, but it's just kind of starting off and illustrating our counting of valence electrons and what have you. Next up, we have some decision making to do in this one. So we're going to draw CO2. The carbon, again, I have 1 of those and it's still got 4 valence electrons, so that's 4. My oxygens, I have 2 of those. Each one has 6 valence electrons, so that gives me 12. So I have 16 electrons altogether, okay? Carbon's the thing there's 1 of. Carbon is the smaller electronegativity. Those things both point to putting carbon in the middle. So I'm going to put carbon at the center, and I'm going to put my oxygens on either side of it, okay? There's nothing really special about putting them on the sides and not putting them like top and bottom or left and top or any of those combinations, right? It's true that I'm drawing these so that my drawing, in this case, I happen to know that in a CO2 molecule, all 3 atoms are in a line. Honestly, if I was going to try and figure that out, if I didn't already just feel like I know that, I would draw the Lewis structure first and then use it to decide. So it's not wrong in any way if you put them in different spots than those 2. I have to attach each oxygen with at least 1 bond, so I do that. At that point, I've used up 4 of my electrons. So now I have a bunch more. I've got 12 more electrons to go, okay? My rule says the next thing I want to do is I want to sprinkle those electrons starting around the outside atoms. So my outer atoms are the 2 oxygens, and my rules said I wanted to put 3 pairs on each one of those as long as I had enough electrons to do that. Here I have exactly enough, right? Because when I do that, I just put 12 dots on there, so that uses up the rest of my electrons, so they're all gone. Now I have to size up my structure, right? Unlike the CH4 case here, I don't just happen to land on something that is a nice, good-looking structure. Why is that? Carbon is in the second row of the periodic table. It's my atom in the middle. It wants to follow the octet rule, okay? The oxygens also want to follow the octet rule, so I want to get 8 electrons around each atom. This provides a little bit of a challenge that we have to resolve because I only have 16 electrons, right? So to get 8 around each of 3 atoms, I have to be double counting some of them. The ones I'm double counting are the ones in the bonds, right? Because right now, if I say the oxygen, say this oxygen over here on the left, I'm going to say that one's got 8 electrons around it because it's got 6 dots and it's got 1 line. So that's 8, right? Also 8 electrons around the oxygen on the right-hand end. My carbon in the middle has only 2 bonds right now, right? So it's only got 4 electrons around it. That's not enough. So I'm going to say, how can I get more electrons to count for the carbon without taking them away from the oxygen? And the answer is, I have to take some that are now dots on the oxygen and make a bond with them, right? So I'm going to take, say, this pair up here, just picking one. It's random where I'm picking, pop them in there. And when I do that, I'll now have 2 bonds on that side of my CO2, right? So now my carbon is up to 6 electrons. It's gotten better. To get 2 more electrons on the carbon, what I have to do is I have to do that again. But here I have 2 choices, right? I could either do this by taking another pair of electrons from the same oxygen, or I could take a pair from the one on the other end. As a general rule, you will almost never go wrong if you opt for the structure that will look more symmetric, okay? Think about it this way. My carbon is making bonds to 2 different oxygen atoms. If I put 3 bonds on one side and just 1 on the other, that says for some reason the carbon is playing favorites between the 2 oxygens, right? It's treating them differently. When in reality, if 2 oxygen atoms come together and approach a carbon atom, the carbon shouldn't be able to tell one from the other. It should want to treat them the same, okay? And I can draw a structure that does that by grabbing a pair of electrons from here and tossing them down there to make another double bond, okay? So when I do that, now I've got a CO2 molecule, and I'll draw a cleaned up version over here that looks like this. And I still got 2 pairs of electrons on my oxygen and 2 over here. Notice that it still doesn't matter what positions I put those dots in, right? So when I was drawing it here, I said I was taking them from the ones on top, and then here I went and put some back on the top and took them from the ends. That makes no difference whatsoever. What's important is that I have 2 bonds on each side, okay? That does turn out to be the best structure for CO2. There's another way we could decide that we like this structure better than the alternative, and I'm about to explain that. So I'll come back to this in a second to use it as an example. A somewhat fancier way to make that decision is to think about what are called formal charges, okay? The formal charge is just a way of counting up electrons. It's not like saying this is the real charge on an atom. I think of it as just an accounting mechanism, a way of keeping score, okay? To find the formal charge on an atom in a structure, what I do is I start with how many valence electrons does that atom have if it's just an atom, just off on its own. So I get that number from where it is in the periodic table, okay? Then I'm going to subtract from that how many valence electrons would I assign to that atom in the structure that I've drawn, okay? When I do this part here, the valence electrons in the structure, I'm going to count differently for this than I do for the octet rule. Now when I have shared electrons, I'm going to divide them down the middle. Why is that? Because I want to count only every electron just once. I want it to be the case that if I add up the formal charges on a neutral molecule, they should sum to 0. Okay, for that to be true, over here, I can only be counting every electron as belonging to one atom or the other. Okay, and if I can find different structures, if I can pick the one that has the smallest or the fewest formal charges, that should be the best one. So let's see how that would work out for my CO2 case. Here, let's start with the structure that I said I wanted us to choose, right? If I pick the oxygens here, my oxygen as an atom, the formal charge is equal to 6 because an oxygen atom has 6 valence electrons if it's a free atom, right? Now to count how many are assigned to it in the structure, I'm going to give it full credit for the dots. There's 4 dots around it, so I'm going to give it 4 for those, and I'm going to count 1 electron for each of the 2 bonds. That makes 6, so I have 6 minus 6, and that equals 0, right? If I did the carbon, my formal charge, if it's a free atom, it's got 4. Again, I get that number from where we are in the periodic table or over here, right? In my structure, it's got 4 bonds, 4 lines, no dots. I count 1 for each bond, so that's 4 minus 4, that's 0 again. All the formal charges are 0, that's a sign that's probably the best structure. Suppose I had taken the 2 pairs of electrons that I was moving and I had taken them from the same end. I would have gotten a structure then that looked like this. If I do that one, the carbon still has 4 bonds, right? So the formal charge on the carbon is still 0. My oxygens now look different from one another, right? If I come down to this one, I would have had a formal charge equal to 6 for a free oxygen atom, minus 2 for the dots, and 1, 2, 3 for the 3 bonds. So now it's 6 minus 5, so that would be plus 1. On this end, I would have a formal charge that was equal to 6 for the free atom, minus 6 for the dots, and 1 for the line, so minus 7. That would be minus 1. Okay. Notice they still add up to 0. They have to add up to 0 as long as I counted every electron just once in there, right? But now I have formal charges that in my top structure did not. And that's another way, sort of a fancier, more elaborate way to decide that I want to choose the structure that has the double bonds on both sides and not the one that has the 2 ends being different. Again, in a lot of cases, you can avoid that just by thinking I want to pick the one that is symmetric, okay? And that'll work for a lot of the structures you'll see in this class. I'm going to draw a structure for sulfur hexafluoride, which is kind of a strange molecule. It's actually a gas at normal temperature and pressure, but it's a very heavy gas. And so, because it's got a high molecular weight. So let's just see what we need for this. Sulfur is underneath oxygen. So I have 1 sulfur atom in here, and it's got 6 valence electrons, so that gives me 6. Fluorines, I have 6 fluorine atoms. Each one has 7 valence electrons because it ends in 2s2, 2p5. That gives me another 42 electrons. So I have 48 electrons altogether. That's kind of a lot, okay? Sulfur definitely has the smaller electronegativity because everything has a smaller electronegativity than fluorine. Sulfur is the thing there's one of, so I'm putting the sulfur in the middle. Next up, I have to get 6 fluorines around my sulfur. So let's start by putting them like I've been on the sides of a square. And then I have to wedge in 2 more just because SF6 does exist. It's a molecule, so I have to be able to make some representation of it. So I'm going to go on the diagonals here and put 2 more in there. Okay. That looks a little strange. I've obviously got more than 8 electrons around my sulfur already, right? Sulfur is deeper in the periodic table. It's in row, the 3rd row, right? And we say it's going to be a bigger atom. It can kind of just accommodate more electrons, right? Remember, as I go down in the column, the atoms get larger. As the atoms get larger, I can sort of fit more bonds around them, just as a spatial argument. That used up, what, 6 times 2? That was 12. So I have 36 more electrons to go. That means I can plop 3 pairs around each of my 6 fluorines, following my rules for drawing the structure. And when I've done that, I will have used up all 36 of my additional electrons. My fluorines all have 8 electrons around them, so they're obeying the octet rule, which is good. They're in row 2. They need to obey the octet rule, okay? My sulfur in the middle is definitely not following the octet rule because it's got 12 electrons around it, right? Because it's got 6 bonds. But I can't not make those 6 bonds because if I don't make those 6 bonds, then my fluorines start falling off, right? So there's no other way to draw a structure for this than to say, well, I guess it can not obey the octet rule. Right? That never happens for, say, carbon, nitrogen, oxygen, those elements in the 2nd row. Those will never have more than 8 electrons around them. Okay, there are a couple of weird structures where especially nitrogen, will end up with an odd number of electrons, and it'll get 7 in that case because it can't go above 8. Okay, we'll probably look at an example of that in class when we are talking about the stuff from this video. Last of my examples, I believe, is ammonium carbonate, okay? The parentheses there on the ammonium ion, I said ion, right? Those are a clue that it's an ion, it's an ionic compound. The carbonate name might also remind you that. So this thing is, basically I'm gonna draw 2 structures. I'm gonna draw one for ammonium for NH4+, I'm gonna draw one for CO3 2-, and then I would just let the ions stick to each other by charges. So let's, over here, let's do NH4+. And so, nitrogen's got 5 valence electrons, so I have one of them times 5, so that's 5. My hydrogens I have 4 of those times 1, so that's 4, right? So right now I'm at 9. But I also have a plus charge, and that plus charge means I have 1 less electron than the atoms would have, right? So I'm going to subtract 1 because of the plus charge. Positive charge means missing an electron, remember, because electrons are negatively charged. That means I have 8 electrons. My nitrogen is the thing that there's 1 of. It's going in the middle. I can't put the hydrogens in the middle after all. I put 4 hydrogens around it. That uses up all 8 of my electrons, and my structure looks, in fact, exactly like CH4 in the beginning. Why does it look like CH4? Because I've still got 8 valence electrons, okay? If I'm being really proper, I should probably take this thing and draw some brackets around it or something like that and put a plus charge up here just to indicate that I know that I've got a number of electrons there that doesn't match what the atoms would have, okay? So that's an ammonium ion. Yes, I could draw another ammonium ion since I have 2 of them in my formula, but that's not really the point of what we're doing. Next, I'm going to work on my carbonate ion. Carbonate is CO3 2-, okay? So my carbon, I have 1 of those, and it's got 4 valence electrons, so that's 4. My oxygens, I've got 3 of those, 6 valence electrons, that's 18, okay? I've got a -2 charge, and that means I've got 2 extra electrons, so I'm going to add 2 in here. When I add all those up, I should have 24 electrons altogether, okay? Carbon goes in the center. I'm going to go for oxygens on 3 spots. Let's go down here, because it's a little further away from where I've got the other one. And I'm going to start off by making bonds to each of those. So I've used 6 electrons. That gives me 18 more to go. We know the system now. We're going to add those as 6 electrons around each of my oxygens. When I get to there, that uses up all my electrons, right? Now I see my oxygens are following the octet rule, but my carbon is not. My carbon has only got 3 bonds around it, okay? 6 electrons. It needs to get 2 more electrons. Just like in the CO2 case, I want to get more electrons on the carbon, but I don't want to lessen the number of electrons I'm counting for the oxygens, okay? How can I do that? Well, I need to make a second bond. I need to move a pair of electrons that currently are a lone pair on oxygen and move them so they're making a bond, okay? You'll notice I missed a pair of electrons down here. That's what you'll notice first. You'll notice that I have 3 choices for where to do that, and it's a totally random and arbitrary choice, okay? So I'm going to take this one just because I feel like it, and I'm going to plop those down here, and when I do that, I get a double bond in that spot. Okay, that gives me a structure that puts a double bond over there. I could just as easily have done that in one of the other spots, okay? So I could have said that one. I could have said I could have drawn one like that. My pencil's failing me again. Or I could have drawn a third one, which I'm going to draw down here because I think it's not going to like me if I try and write over there. And now I've got to go. Okay, it's just not wanting to write anywhere right now. And I'll try and be good and put in all the electrons, although I'm kind of getting tired of drawing dots. Right, so I could have drawn any one of these 3 structures. There's not like a right one to pick or a wrong one to pick because there's no difference, right? It's totally an arbitrary choice. When you get to a spot where you have that, we'll come back to this to finish in a second. This is the situation where we draw what we call resonance structures, okay? That says I have multiple different structures that I could draw and they're equally good. Those 3 versions of the carbonate structure I just drew, there's nothing any better or worse about one of them than the other, okay? So those 3 equivalent structures, what we end up doing to represent this is we actually draw all 3 of them. And we say that the actual ion, in this case, the actual structure, is a hybrid of those 3 things. Okay, this is a way to try and make the Lewis structure idea work for things that it just isn't really great at. okay? The real molecule, or in this case, the real ion, does not actually just change its structure between those things. It's a constant structure, and it's just in between all those. What do I mean by that? I mean, if I come back here, and this thing, yeah, to do this right, I'd do something like put a set of arrows maybe in here that say they're all contributing to the structure, right? And it's kind of gawky looking by now, particularly because I drew these kind of large. And then if I'm being, again, careful, I could take all that and put them inside something and label them as having a 2- charge, right? What do I mean when I say that the molecule, the ion, isn't changing structure? If any one of those structures was right, then my carbonate ion would have one bond that was stronger than the others, because the one that has 2 pairs of electrons shared, that should pull the atoms tighter together, okay? And so in that case, my ion itself would have bonds that I could tell the difference between them, right? By measuring how far apart the atoms were, or by measuring how strong the bond was. We'll talk soon about ways to measure those sorts of things, okay? If in fact I measure a carbonate ion, all 3 carbon to oxygen bonds in it are indistinguishable. They're all identical to each other, okay? So it's kind of like it's the average of those 3 structures. One way of talking about this is, instead of saying like this, if I call this a double bond and this a single bond, right? Instead of saying I have 2 single bonds and a double bond, I could say that I have 3 different bonds, and on average, they're all like 1 1/3 bonds, because I have 4 bonds smeared out or spread out among those 3 places, okay? We'll eventually talk about a way to explain that and make sense of it. For now, when you're drawing one of these structures, if you come to a spot where you're making a choice between 2 different options, or 3 different options in this case, and it feels like there's no basis on which to decide, that should be your cue to say, I'm probably supposed to draw resonance structures for this, to acknowledge that all of those different structures are possible.